Okay, our warm-up today is on the Boltzmann distribution, okay, for an ideal gas. And we have three different samples of gases, all the same number of molecules total in the gas, but at different temperatures. So flask A is at 300 Kelvin, flask B is 200 Kelvin, and flask C is 400 Kelvin. And they are all at, the same conditions other than the temperature, same molecules, and they're all oxygen gas. The Boltzmann distribution is a graph of probability, or maybe total number of molecules on the y-axis. And then the x-axis can be velocity or kinetic energy. We noticed that, for 300 Kelvin, which would be flask A, we've got a nice rise here to the peak velocity. That would be the greatest velocity that the particles have through the VRMS, which is the root mean square average, okay, for the velocities. And then, it does slide down here, okay, towards the end there where there's higher kinetic energy, okay, for the molecules. But we see that that's low probability. So what I want you to do is make a prediction. What would the sketch of the 200 Kelvin gas look like on here? And what would the 400 Kelvin look like on here? So pause the video, make your guesses, and then restart afterwards and see if you're right. Okay, now I'm assuming that you did, pause the video. And here's what it should look like. So we're going to see that there is another rise here very quickly. But our peak is going to probably be a little bit higher. And it's going to peak earlier. Okay, I'm just going to do dashed lines here to help me do this. Okay, and have some kind of a graph like this. So we're going to see a shift left because now at a cooler temperature, more gas molecules will probably have less velocity since it's a cooler gas. Now what about the 400 Kelvin? Well, we're going to see a stretching out of the graph as it goes this way. It's going to peak somewhere out here, and it won't be as tall. Okay, so we're going to shift this to the right and not be as tall. So it looks something like this. As more of the gas molecules shift, okay, towards the greater velocity or greater energy end of the curve. So that's what they would look like. So this one is going to be graph B, and this one, of course, is graph C, and the original graph was graph A. Now what about that VRMS, calculation there? So the root mean square average, VRMS, for the molecules in a gas is governed by the equation, the square root of 3RT, okay, divided by molecular mass. So let's do that for the 300 Kelvin sample. So the root mean square average of the velocity is then going to be equal to the square root of 3 times 8.31 times the temperature in Kelvin of 300. And we'll divide this by the molecular mass of 32. And that'll give us 15 meters per second, the two significant digits. So if we can go back to our original graph, that means 15 meters per second is located right here. Okay, now let's change the conditions here and say that all of these guys are placed in an environment outside that is 300 Kelvin. And we want to let them, sit in that environment until they all reach thermal equilibrium. Now, what's going to happen to the kinetic energy averaged for each flask? Let's go A, B, and C. All right, I'll pause the video, make your guesses. This shouldn't take very long, but try it. And then restart the video and see if you're right. Okay, now assuming that you did pause the video, let's look at the flask A. Flask A is going to see no change in the average kinetic energy because we're going to assume that the 300 degrees, they're all going to reach equilibrium with the 300 Kelvin. Okay, the 200 Kelvin, of course, is going to increase because heat should flow into that. So we are going to see an increase in kinetic energy for the flask. And then the 400 is then going to cool down. It's going to lose heat, okay, to the environment. So we should see a decrease in the average kinetic energy for flask C. And our next unit, we will take a look at how the entropy changes, okay, for each of the flasks. You can probably guess that the entropy for A would have no change. The entropy for B will be increased, and the entropy for C will decrease. And if you're guessing that right now, you would be correct, because entropy is disorder, and disorder is temperature dependent.